Let's start with something simple. You're lying there right now, breathing quietly, maybe pulling the covers up a little higher, and every single atom in your body is made of matter. The pillow under your head, the air filling your lungs, the walls around you, the planet beneath you, the moon overhead, the sun that will come up in a few hours. All of it, every last bit, is matter. Protons, neutrons, electrons, all assembled into atoms, all behaving the way matter behaves. And that probably doesn't sound surprising. Of course, everything is made of matter. What else would it be made of? But here's the thing. There's another kind of stuff. Not dark matter. Not some exotic hypothetical. Something we've actually made. Actually held in magnetic traps. Actually photographed and measured and weighed. It's called antimatter. And it is, in almost every respect, a perfect mirror image of the matter you're made of. For every particle of matter, there exists, or at least there can exist, an antiparticle. An electron has an anti-electron. A proton has an antiproton. A quark has an antiquark. They have the same mass, the same spin, the same everything, except their charges are flipped. Where one is negative, the other is positive. Where one has a certain kind of quantum number, the other has the opposite. And if you bring a particle and its antiparticle together, if you let them touch, even for an instant, they annihilate each other. Both of them vanish, and all of their mass converts into pure energy. Not some of it, all of it. A flash of gamma rays, clean and total, governed by Einstein's most famous equation, E equals mc squared. The mass of both particles multiplied by the speed of light squared, released as energy. And because the speed of light is such an enormous number, even a tiny amount of antimatter annihilating with matter releases a staggering quantity of energy. So antimatter is real. It exists. We can make it. We have made it. And at first glance, it seems like the universe should have made equal amounts of both, matter and antimatter, side by side, in perfect balance. After all, the laws of physics don't seem to prefer one over the other. The equations work the same way in both directions. When the universe was born, in the unthinkable heat of the Big Bang, matter and antimatter should have been created in exactly equal quantities, perfectly paired, perfectly symmetrical. But look around. Everything you see is matter. The stars, the galaxies, the gas clouds between them, all matter. If the universe had truly made equal amounts of both, they would have annihilated each other completely. Every particle would have found its antiparticle, and they would have destroyed each other, leaving behind nothing but a sea of light. No atoms, no stars, no planets, no you, no me. Just photons, just radiation, just an empty, glowing void. And yet here we are. Somehow, at some point in the first fractions of a second after the Big Bang, something tipped the balance. Something, and we genuinely do not know what, created a tiny, almost imperceptible excess of matter over antimatter. For every billion pairs of particles and antiparticles that annihilated each other, there was roughly one extra particle of matter left over. 1 in a billion. A rounding error in the cosmic ledger. And that rounding error is everything. That leftover residue, that slight, unexplained imbalance, is the stuff that makes up every galaxy, every star, every planet, every living thing. You exist because of a cosmic asymmetry so small it's almost invisible, and nobody can fully explain why it happened. So tonight, that's what we're going to explore. What antimatter actually is. Not in a hand-wavy, science fiction kind of way, but what it's genuinely made of, how we know it exists, what happens when it meets matter, and why the universe seems to have systematically destroyed almost all of it. And along the way, we're going to meet some remarkable people, a quiet, brilliant mathematician who predicted antimatter before anyone had ever seen it, a young experimenter who found it hiding in cosmic rays, and generations of physicists who have been chasing one of the deepest unsolved mysteries in all of science. Because the question of why there's more matter than antimatter isn't just a curiosity. It's the question of why anything exists at all. Let's start at the very beginning. Not the beginning of the universe, but the beginning of the idea. Because antimatter wasn't discovered in a lab, it was discovered on paper, by a man who was trying to solve an entirely different problem, and stumbled into something that changed everything we thought we knew about reality. The year is 1928, and the man is Paul Dirac. He's in his mid-20s, working at the University of Cambridge, and he's already considered one of the most gifted theoretical physicists alive. Dirac is, by all accounts, extraordinarily quiet. He almost never speaks, unless he has something precise to say. His colleagues sometimes joke that a dirac is a unit of measure for the fewest words per hour. He's awkward in social situations, intensely focused, and almost supernaturally good at mathematics. And in 1928, he's trying to solve a problem that's been nagging at the physics community for a few years. The problem is this: quantum mechanics, which had been developed over the previous decade by people like Heisenberg and Schrödinger and Born, was incredibly successful at describing how particles behave at very small scales. Schrödinger's equation, in particular, could predict the behavior of electrons in atoms with remarkable accuracy. But Schrödinger's equation had a limitation. It didn't account for special relativity. It worked fine for slow-moving particles, but electrons in atoms can move at significant fractions of the speed of light, and at those speeds, you need Einstein's relativity to get the right answers. So physicists knew they needed an equation that combined quantum mechanics with special relativity, a relativistic quantum equation for the electron, and Dirac set out to find it. Not because he wanted to discover antimatter, he had no idea that was coming, but because he wanted an equation that was both quantum mechanical and relativistically correct. And what he came up with was one of the most beautiful pieces of mathematics in the history of physics, the Dirac equation. It's written in a compact, elegant form, and it did exactly what he wanted. It described the electron in a way that was consistent with both quantum mechanics and special relativity. It predicted the electron's spin, which had been observed experimentally but never explained theoretically. It got the magnetic properties of the electron right. It was, by every measure, a triumph. But it had a problem, or rather, it had an extra solution. You see, the Dirac equation is a lot like a quadratic equation in that it has more than one solution. When you solve x squared equals 4, you get two answers, positive 2 and negative 2. Both are mathematically valid, and when Dirac solved his equation for the energy of an electron, he got two sets of solutions. One set described electrons with positive energy, normal electrons, behaving the way electrons should. The other set described something with negative energy, and that was deeply strange. What would a negative energy electron even mean? It seemed like nonsense. If negative energy states existed, then ordinary electrons should be able to fall into them, releasing energy as they dropped, and they'd keep falling, spiraling down into ever more negative energies, releasing infinite amounts of energy in the process. The universe would be catastrophically unstable. Obviously, that doesn't happen. So what was going on? Dirac, being Dirac, didn't just wave the negative energy solutions away. He took them seriously. And in 1930, he proposed one of the most audacious ideas in the history of physics, the Dirac sea. He suggested that all those negative energy states were already filled, every single one of them, occupied by an electron you couldn't see. The vacuum, in Dirac's picture, wasn't empty. It was a vast, infinite sea of negative energy electrons, packed in so tightly that you couldn't detect them because they were everywhere, uniform and featureless, like water you've been swimming in your whole life. But here's where it gets fascinating. Dirac realized that if you could somehow knock one of those negative energy electrons out of the sea, if you could give it enough energy to jump up into a positive energy state, you'd create two things simultaneously. You'd have the electron itself, now visible as a normal positive energy electron, and you'd also have a hole in the sea, a gap where a negative energy electron used to be. And that hole, Dirac realized, would behave exactly like a particle, but with the opposite charge. A hole in a sea of negative electrons would look positive. It would have the same mass as the electron, the same spin, the same everything, except its charge would be reversed. At first, Dirac hoped that these holes might be protons. Protons are positive, after all, and they were the only positive particles known at the time. But the math didn't work. The holes had to have the same mass as the electron, and protons are nearly 2,000 times heavier. So Dirac was forced to a remarkable conclusion. His equation predicted the existence of a completely new particle. A particle exactly like the electron, but with a positive charge. An anti-electron. And here's what's wild about this. He predicted it purely from mathematics. Nobody had ever seen such a thing. Nobody had ever imagined such a thing. The idea that every particle might have a mirror twin with opposite charge was not on anyone's radar. It emerged, unbidden, from the internal logic of the equation itself. The mathematics demanded it. And that's one of those moments in physics that gives you chills, if you think about it. The equations describing reality contained, hidden within them, the prediction of something no one had ever observed. Nature had written the answer into the math, and Dirac was the first person to read it. But predictions are just predictions until someone actually finds the thing in question, and the physics community was skeptical. Dirac's idea was bizarre. An anti-electron, a sea of invisible particles filling all of space. It sounded more like science fiction than science. People respected Dirac's mathematics, but the physical interpretation made a lot of them uncomfortable. Some thought the negative energy solutions were just mathematical artifacts, quirks of the equation that didn't correspond to anything real. And then, in 1932, everything changed. Carl Anderson was a young physicist at the California Institute of Technology, and he was studying cosmic rays. Cosmic rays are high-energy particles that come streaming in from outer space, protons and atomic nuclei mostly, accelerated to incredible speeds by violent astrophysical events, like supernovae and the jets of black holes. When these particles hit the upper atmosphere, they collide with air molecules and produce showers of secondary particles that rain down toward the ground. In the early 1930s, cosmic rays were one of the only sources of high-energy particles available to physicists. Particle accelerators were still in their infancy, so if you wanted to study exotic particles, you looked up. Anderson had built a cloud chamber, a sealed container filled with supersaturated vapor, so that when a charged particle zipped through it, it left a trail of tiny droplets in its wake, a visible line, like a contrail behind a jet. By placing the cloud chamber inside a strong magnetic field, Anderson could make the particle trails curve. Positively charged particles curved one way, negatively charged particles curved the other, and the tightness of the curve told you something about the particle's momentum. Lighter, slower particles curved more tightly, while heavier, faster ones bent only slightly. In August of 1932, Anderson photographed something he couldn't explain, a track in his cloud chamber that curved the wrong way. It had the curve of an electron, the same mass, the same gentle arc, but it was bending in the direction that a positive charge would bend. not a proton. A proton would have left a much thicker, less curved track because of its much greater mass. This was something with the mass of an electron, but the charge of a proton, an anti-electron, exactly what Dirac's equation had predicted. Anderson called it the positron, and just like that, antimatter went from a wild mathematical prediction to a confirmed physical reality. The positron was real. It existed in nature. Cosmic rays were producing them in the upper atmosphere all the time, matter and antimatter being created together, right over our heads, as high-energy particles smashed into air molecules. Anderson won the Nobel Prize in Physics for the discovery in 1936. He was just 31 years old. And interestingly, Anderson later said he hadn't been particularly aware of Dirac's prediction when he made the discovery. He found the positron experimentally, and only afterward connected it to Dirac's theory. Sometimes science works that way. Theory and experiment converge from different directions, and the universe says yes, both of you were right. Now, let's pause here for a moment and think about what this means. Because the discovery of the positron wasn't just the discovery of a new particle. It was the discovery of a new category of existence. If the electron has an antiparticle, what about the proton? What about the neutron? What about every other particle? Dirac's equation was specifically about electrons, but the logic behind it, the requirement that relativistic quantum equations have both positive and negative energy solutions, applied much more broadly. And over the following decades, physicists found antiparticle after antiparticle. The antiproton was discovered in 1955 at the Bevatron Particle Accelerator at the University of California, Berkeley. Emilio Segre and Owen Chamberlain led the experiment, and they won the Nobel Prize for it in 1959. The antineutron was found the following year, in 1956, at the same facility. And as particle physics expanded through the 1950s, 60s, and 70s, discovering more and more particles, muons, pions, kaons, neutrinos, quarks, every single one of them turned out to have an antiparticle. No exceptions. It's one of the most reliable rules in physics. Every particle of matter has a corresponding antiparticle of antimatter, with the same mass and opposite charge. And that brings us to a question that's both simple and deep. What is antimatter actually made of? Not metaphorically, literally. What is a positron? What is an antiproton? What are they made of at the most fundamental level? Here's the first thing to understand, and this is important, because a lot of people get it slightly wrong. Antimatter is not made of some exotic, otherworldly substance. It's not negative matter. It's not phantom matter. It's not some kind of shadow stuff from another dimension. Antimatter is made of the same fundamental ingredients as matter. It's made of quarks, antiquarks specifically, and leptons, antileptons, the same families of particles, governed by the same forces, described by the same equations. Let's break that down. In ordinary matter, a proton is made of 3 quarks, 2 up quarks and 1 down quark, bound together by the strong nuclear force. An antiproton is made of 3 antiquarks, 2 anti-up quarks and 1 anti-down quark, also bound together by the strong force. The antiquarks have the same masses as their matter counterparts, but their electric charges are flipped. An up quark has a charge of positive 2/3. An anti-up quark has a charge of negative 2/3. A down quark has a charge of negative 1/3. An anti-down quark has a charge of positive 1/3. So when you add them up, 2 anti-ups and 1 anti-down, you get a total charge of negative 1, which is exactly the charge of an antiproton, the mirror image of the proton's positive 1. The same pattern holds for the antineutron. A regular neutron is made of 2 down quarks and 1 up quark. and their charges add up to 0. An antineutron is made of 2 anti-down quarks and 1 anti-up quark, and their charges also add up to 0. So the antineutron is electrically neutral, just like the neutron. But it's still different. Its constituent quarks carry the opposite color charges, which is a quantum property related to the strong force, not actual colors. And its magnetic moment points the other way. It's a distinct particle, even though it has the same mass and the same electric charge as a neutron. Think about that for a second. You could, in principle, build an anti-atom, take an antiproton, which has a negative charge, and let a positron orbit around it, attracted by the electromagnetic force, just the way an electron orbits a proton. What you'd have is antihydrogen, a complete atom of antimatter, and it would behave, as far as we can tell, almost identically to ordinary hydrogen. It would absorb and emit light at the same frequencies. It would form anti-molecules if you had enough of it. You could, in theory, build an entire anti-world. Anti-stars, anti-planets, anti-oceans, anti-people. And from the inside, it would look completely normal. The chemistry would work the same. The biology would work the same. Light would behave the same. You wouldn't be able to tell, from the inside, that you were made of antimatter. In fact, physicists at CERN, the European Organization for Nuclear Research in Geneva, have actually made anti-hydrogen atoms. The first few were created in 1995, and since then, experiments like Athena, Atrap, and Alpha have produced thousands of them, trapped them in magnetic bottles, and studied their properties. The Alpha experiment, in particular, has measured the spectrum of anti-hydrogen, the specific wavelengths of light it absorbs and emits, and compared it to ordinary hydrogen. And so far, the results are identical, to a very high degree of precision. Antimatter really does look like a perfect mirror image of matter. And that, right there, is the heart of the mystery. If antimatter is just matter, with some signs flipped, if it obeys the same laws, has the same mass, forms the same structures, then why is there so much more matter than antimatter in the universe? Why isn't the universe 50-50? Why didn't equal amounts of both survive the Big Bang? Let's go back to the very beginning. Not 1928, not Dirac's equation. The very beginning. The Big Bang itself. About 13.8 billion years ago, the universe began in a state of unimaginable heat and density. We're talking temperatures so high that ordinary language breaks down. Trillions of degrees. Conditions so extreme that the fundamental forces of nature were unified. Particles didn't have mass yet, and the distinction between different types of forces didn't exist. In that first instant, the universe was a seething, roiling soup of energy, and as it expanded and cooled, particles began to crystallize out of that energy, the way snowflakes form as water vapor cools. And here's the key point. When energy converts into matter, the laws of physics as we understand them require that matter and antimatter be produced in exactly equal amounts. This is a fundamental symmetry of the equations. If a photon, a particle of light, has enough energy, it can spontaneously produce a particle-antiparticle pair, an electron and a positron, say, or a quark and an antiquark, always in pairs, always balanced. The universe doesn't make matter without making antimatter. It's built into the mathematics at the deepest level. So in those first fractions of a second after the Big Bang, the universe was filled with roughly equal numbers of particles and antiparticles, quarks and antiquarks, electrons and positrons, neutrinos and antineutrinos, all being created from the intense energy of the expanding fireball, all smashing into each other, annihilating, and being recreated again in a furious cycle of creation and destruction. Now, As the universe expanded, it cooled. And as it cooled, the energy available for creating new particle-antiparticle pairs dropped. There came a point, very early, within the first few seconds, when the temperature dropped below the threshold needed to produce quarks and antiquarks from pure energy. At that point, the music stopped. The existing quarks and antiquarks could no longer be replenished, and they started annihilating each other for the last time. Each quark finding an antiquark, merging, vanishing into gamma rays. If the numbers had been exactly equal, if there had been precisely one antiquark for every quark, they would have annihilated perfectly. Every quark would have found its partner, and the result would have been a universe with no matter at all. Just photons. Just a uniform bath of electromagnetic radiation, gradually cooling as the universe expanded. No atoms, no molecules, no chemistry, no stars, no planets, no life. Nothing you could stand on, nothing you could hold. Just light, forever. But that's not what happened. And this is where it gets strange. Somehow, and I want to emphasize that word, somehow, because we genuinely do not have a complete explanation, there was a tiny excess of matter over antimatter. For every billion antiquarks, there were 1,000,000,001 quarks. Just one extra in every billion. An asymmetry so small that it's hard to even conceptualize. If you imagine 1,000,000,000 red balls and 1,000,000,000 blue balls in a room, the asymmetry is like adding one additional red ball. You'd barely notice. But when all the red and blue balls pair up and annihilate each other, 1 in 1,000,000,000 red balls is left over. And that leftover residue, that 1 in 1,000,000,000 cosmic rounding error, is everything. Every galaxy you've ever seen in a photograph, every star in the night sky, the sun, the earth, the oceans, the mountains, the forests, the bacteria, the whales, the people, you, all of it is that tiny remainder, the leftovers from the great annihilation. And the photons? The gamma rays produced by all those annihilations? They're still here too. They've been traveling through the expanding universe for 13.8 billion years, stretching and cooling as space itself expanded. Until today, they've redshifted all the way down to microwaves. They're the cosmic microwave background radiation, that faint, uniform glow that fills all of space, first detected by Arno Penzias and Robert Wilson at Bell Labs in 1965. When you look at the cosmic microwave background, you're literally seeing the afterglow of all that matter-antimatter annihilation, the remnant light from the destruction of almost everything. So let's sit with that for a second. The universe made equal amounts of matter and antimatter. They destroyed each other, almost completely, and the tiny scrap that survived, less than 1 part in 1,000,000,000, is the entire physical universe as we know it. Everything that exists is a rounding error, and the question, the really deep question, the one that has kept physicists up at night for decades, is why? Why was there that tiny excess? What broke the symmetry between matter and antimatter? What tipped the scales so that matter won, even by that vanishingly small margin? This question has a name. It's called the baryon asymmetry problem, or sometimes the matter-antimatter asymmetry. Baryons are particles made of 3 quarks. Protons and neutrons are the most familiar examples. And the problem is why the universe contains baryons but essentially no antibaryons. We see matter everywhere we look. We do not see antimatter, not in significant quantities, not in the form of anti-stars or anti-galaxies or anti-anything. The antimatter is gone, destroyed. And the question is, what gave matter its tiny advantage? To start understanding this, we need to talk about symmetry. Not symmetry in the everyday sense, like a butterfly's wings or a snowflake, but symmetry in the physics sense. Symmetries in physics are about the rules of the game. They're about what you can change without changing how the laws of nature work. And for a long time, physicists assumed that certain symmetries were absolutely sacred, that the universe was perfectly fair in some deep, fundamental way. There are 3 symmetries that are particularly relevant here, and they go by the letters C, P, and T. C stands for charge conjugation. This is the operation where you replace every particle with its antiparticle, swap all the charges, flip matter into antimatter, and vice versa. If the laws of physics obey C symmetry, then the universe should behave exactly the same way if you replaced all matter with antimatter. Everything would work identically. P stands for parity. This is essentially a mirror reflection. It's the operation where you flip all the spatial coordinates, turning left into right and right into left. If the laws of physics obey P symmetry, then the mirror image of any physical process should also be a valid physical process. The universe should look the same in a mirror. T stands for time reversal. This is the operation where you run the movie backward, reverse the direction of time. If the laws of physics obey T symmetry, then every physical process should work just as well in reverse. A ball bouncing off the floor should look just as natural when you play the film backward. For a long time, physicists believed that all 3 of these symmetries were exact, that the universe genuinely didn't distinguish between matter and antimatter, between left and right, between past and future, at the level of fundamental laws. And this belief wasn't just aesthetic, it was supported by experiment. Every process that had been studied seemed to obey all 3 symmetries perfectly. And then, in 1956, everything started to unravel. The trouble began with a puzzle involving kaons, particles that are heavier than protons and are produced in high-energy collisions. There were 2 types of kaon that seemed to have identical masses and identical properties, but decayed in different ways. One into 2 pions, the other into 3. This was called the theta-tau puzzle, and it was deeply confusing, because if the 2 particles were really the same, they should decay the same way. But if they were different, why were all their other properties identical? 2 young Chinese-American physicists, Tsung-Dao Li and Chen-Ning Yang, proposed a radical solution. Maybe the 2 particles were actually the same particle. And maybe the reason they could decay in 2 different ways was that the weak nuclear force, the force responsible for radioactive decay, didn't respect parity symmetry. Maybe the weak force could tell the difference between left and right. Maybe, when it came to the weak interaction, the mirror image of a physical process was not always a valid physical process. This was shocking. Parity symmetry had been a bedrock assumption for decades. Li and Yang were essentially suggesting that the universe has a built-in handedness, that at the fundamental level, nature is not perfectly symmetrical between left and right. And here's what makes this story great. They didn't just theorize. They proposed specific experiments to test the idea. And the experiments were done almost immediately, primarily by a brilliant experimentalist named Chien-Shiung Wu, who was at Columbia University at the time. Wu's experiment, published in early 1957, was elegant and devastating. She took a sample of cobalt-60, a radioactive isotope, cooled it to very near absolute zero to minimize thermal motion, and placed it in a magnetic field to align the nuclear spins. Then she watched which direction the electrons came out when the cobalt atoms decayed via the weak force. If parity were conserved, if the weak force treated left and right equally, the electrons should have come out equally in both directions, symmetric, no preference. But that's not what Wu found. The electrons came out preferentially in one direction. there was a clear, measurable asymmetry. The weak force does distinguish between left and right. Parity is violated. This was one of those moments that shakes the foundations. Li and Yang won the Nobel Prize in 1957, the same year the result was announced. Wu, tragically, was not included in the Nobel Prize, despite having done the experiment that proved the theory. It remains one of the most egregious omissions in Nobel history, and it's worth pausing on that, because the stories of the people who do the work but don't get the credit are also part of the history of physics. Now, the violation of parity was a bombshell, but physicists quickly found a way to patch things up. They proposed that even though p symmetry is violated, a combined symmetry called CP, the combination of charge conjugation and parity, might still be preserved. The idea is this: if you flip left and right and swap matter for antimatter simultaneously, maybe everything still works out. Maybe nature isn't fair about left versus right, and isn't fair about matter versus antimatter, but it's fair about the combination, like a two wrongs make a right kind of symmetry. And for a while, CP symmetry seemed to hold. Every experiment testing it came back clean. Physicists breathed a sigh of relief. The universe was still symmetric in some deep sense. Not perfectly, not in the simple way they'd hoped, but in this more subtle, combined way. CP symmetry was the new bedrock. And then came 1964. James Cronin and Val Fitch, working at Brookhaven National Laboratory on Long Island, New York, conducted an experiment that would change everything. They were studying neutral kaons, specifically, the way neutral kaons decay, and they found something that should not have been there. The experiment itself is technical, but the key idea is beautiful. Neutral kaons are strange particles, in both the colloquial and technical sense of the word. There are two types of neutral kaon, which physicists call K-long and K-short, based on their lifetimes. K-short decays quickly, mostly into two pions. K-long lives much longer and decays into three pions. If CP symmetry were exact, if the combined operation of swapping matter with antimatter and left with right were a perfect symmetry, then K-long should never, ever decay into two pions. That decay channel should be absolutely forbidden. But Cronin and Fitch found that, very rarely, about 2 times out of every 1,000 decays, K-long did decay into two pions. It was a tiny effect, barely detectable, easy to miss if you weren't looking carefully. But it was there, unmistakable, real. CP symmetry was not perfect. It was violated. And this, let me tell you, is one of the most important experimental results in the history of physics. It doesn't sound dramatic. A particle decays in a slightly unexpected way, 2 times out of 1,000. But think about what it means. CP violation means that the laws of physics are not perfectly symmetric between matter and antimatter, even when you account for the mirror flip. Nature has a built-in, fundamental preference. It treats matter and antimatter slightly differently. Not by much. The effect Cronin and Fitch found was tiny. But it's there. Cronin and Fitch won the Nobel Prize in 1980 for this discovery. And the reason it's so important goes all the way back to our central mystery. Why is there more matter than antimatter in the universe? Because CP violation is one of the necessary ingredients for creating that asymmetry. This connection was made explicit by a remarkable Soviet physicist named Andrei Sakharov. Sakharov is famous for many things. He was the father of the Soviet hydrogen bomb and later became a dissident and human rights activist, winning the Nobel Peace Prize in 1975. But in 1967, he published a paper laying out the 3 conditions that must be satisfied for the universe to develop an asymmetry between matter and antimatter, starting from an initially symmetric state. These are now known as the Sakharov conditions, and they are one of those moments where physics achieves a kind of crystalline clarity. Here they are, in plain language. First, there must exist processes that violate baryon number conservation. In other words, there must be some physical process that can create more baryons than antibaryons, or vice versa. Baryon number is a kind of bookkeeping device. Every proton and neutron counts as +1. Every antiproton and antineutron counts as -1. And in most physical processes, the total baryon number is conserved. If you start with a baryon number of 0, you end with a baryon number of 0. But if you want to end up with more matter than antimatter, you need some process that can change the total baryon number, something that creates a net excess of matter. Second, there must be CP violation. This is exactly what Cronin and Fitch discovered. If the laws of physics were perfectly symmetric between matter and antimatter, even with the parity flip, then any process that created an excess of matter would be exactly balanced by an equally likely process that created an excess of antimatter. The net effect would be 0. CP violation breaks that balance. It means that the rates of matter-producing and antimatter-producing processes can be different. The universe can prefer one over the other. Third, these baryon number violating, CP violating processes must occur out of thermal equilibrium. This is a subtle but crucial point. In thermal equilibrium, when a system is perfectly balanced and all processes are occurring at the same rate as their reverse processes, no net asymmetry can build up. Even if individual reactions create more matter than antimatter, the reverse reactions would undo the effect just as quickly. You need a departure from equilibrium, a moment when the system is out of balance, cooling rapidly, or undergoing a phase transition, for the asymmetry to freeze in and become permanent. So to get a universe full of matter, and essentially no antimatter, you need all three ingredients: baryon number violation, CP violation, and departure from thermal equilibrium. Without any one of them, the asymmetry can't develop. And the beauty of Sakharov's conditions is that they tell you exactly what to look for. If you want to solve the mystery of why there's more matter than antimatter, you need to find the specific physical processes that satisfy all three conditions. Now, here's the thing, and this is where the mystery deepens. We know CP violation exists. Cronin and Fitch proved it in 1964, and since then, it's been observed in many other systems, in B mesons, in D mesons, in other kaon experiments. And it's built into the standard model of particle physics through something called the CKM matrix, which describes how quarks of different types mix with each other during weak force processes. The CKM matrix contains a parameter, a complex phase, that is the source of CP violation in the standard model. And it's been measured. It's real. But here's the problem. It's not enough. The amount of CP violation in the standard model is far, far too small to explain the observed asymmetry between matter and antimatter in the universe. When physicists do the calculation, taking the known CP violation in the CKM matrix and plugging it into models of the early universe, they get an asymmetry that is many orders of magnitude too small, something like 10 orders of magnitude, maybe more. The standard model predicts a universe that is almost perfectly symmetric, far more symmetric than what we actually observe. The tiny CP violation we've measured can't account for the fact that you exist. And this is one of the great unsolved problems in physics. It's not like we have no clue. We have the Sakharov conditions. We know the ingredients. We've measured some CP violation. But the known sources of CP violation aren't powerful enough. Something else must be contributing. Some unknown physics, beyond the standard model, must be providing additional CP violation. or satisfying the Sakharov conditions in some way we haven't figured out yet. Let's talk about some of the ideas people have had, because they're fascinating. And honestly, this is one of those areas where you can feel the frontier, where established knowledge meets speculation, and physicists are genuinely groping in the dark, trying to figure out what happened in the first fractions of a second after the Big Bang. One idea is called electroweak baryogenesis. The concept is that during the very early universe, as it cooled from its initial extreme temperatures, it underwent a series of phase transitions, a bit like water, freezing into ice, but much more dramatic. One of these phase transitions involved the electroweak force, which is the unified version of the electromagnetic force and the weak nuclear force. At very high temperatures, these two forces are unified into a single electroweak force. As the universe cooled below a certain temperature, roughly 1,000 trillion degrees, or about 1/10 trillionth of a second after the Big Bang, the electroweak force broke apart into the separate electromagnetic and weak forces we see today. This is called electroweak symmetry breaking, and it's one of the most important events in the history of the universe. During this phase transition, conditions were wildly out of thermal equilibrium. Bubbles of the new, broken symmetry phase were nucleating and expanding, sweeping through the universe like bubbles forming in boiling water. And at the boundaries of these bubbles, the walls where the old phase met the new phase, all sorts of exotic physics could occur. Particles crossing the bubble wall would interact with the changing fields in complex ways, and in principle, these interactions could produce a net excess of baryons over antibaryons. The idea is beautiful, and it satisfies all three Sakharov conditions. There are processes that violate baryon number, called Sphaleron processes, which are a genuinely weird feature of the electroweak theory. There's CP violation in the interactions at the bubble wall, and the whole thing is happening out of equilibrium. But when you do the detailed calculations with the standard model, the numbers don't work out. The phase transition in the standard model isn't dramatic enough. It's a smooth crossover rather than a sharp first-order transition, and the CP violation is too weak. You need extensions of the standard model, new particles, new interactions, new sources of CP violation, to make electroweak baryogenesis work. Another idea, and one that many physicists find particularly elegant, is called leptogenesis. This idea, proposed by Masataka Fukugita and Tsutomu Yanagida in 1986, starts not with baryons, but with leptons, the family of particles that includes electrons and neutrinos. The idea is that in the very early universe, extremely heavy particles called heavy right-handed neutrinos existed. These particles are not part of the standard model. They're hypothetical, predicted by various extensions of the standard model, and they're believed to have been incredibly massive, perhaps 1 trillion times heavier than a proton. These heavy neutrinos, the theory goes, decayed in the early universe, and their decays violated CP symmetry, producing slightly more leptons than antileptons. This created a net lepton asymmetry, and then, through the same Sphaleron processes I mentioned earlier, those weird baryon number violating interactions of the electroweak theory, this lepton asymmetry was partially converted into a baryon asymmetry. So you end up with more matter than antimatter, even though the original imbalance was in the lepton sector, not the baryon sector. Leptogenesis is appealing because it connects the matter-antimatter asymmetry to the physics of neutrinos, which are themselves deeply mysterious particles with lots of unanswered questions. And there's a tantalizing connection. The fact that neutrinos have mass, which was confirmed experimentally around 1998, is itself evidence for physics beyond the standard model, and the most popular explanation for why neutrinos are so light, something called the seesaw mechanism, naturally introduces the very heavy right-handed neutrinos that leptogenesis requires. But here's the challenge. The heavy right-handed neutrinos, if they exist, are far too massive to be produced in any particle accelerator we have or could build in the foreseeable future. So we can't directly test leptogenesis. We can look for indirect evidence, for CP violation in the neutrino sector, for example, which experiments like T2K in Japan, NOVA in the United States, and the upcoming DUNE experiment at Fermilab are actively searching for. But a direct confirmation may be beyond our current experimental reach. And this is the frustrating, beautiful reality of modern physics. Some of the most important questions. Why is there something rather than nothing? What tipped the balance in favor of matter? What happened in the first trillionth of a second after the Big Bang may involve physics at energy scales so far beyond what we can probe in the lab that we have to rely on indirect evidence, clever theoretical arguments, and the study of the universe itself as our laboratory. But let me come back to antimatter itself, because there's still so much to say about what it is, how it behaves, and what we've actually done with it. And some of it is genuinely astonishing. Let's talk about what happens when antimatter meets matter. I mentioned annihilation earlier, but let's really dig into it, because the physics of annihilation is one of the most remarkable things in nature. When an electron meets a positron, its antimatter counterpart, they annihilate each other. Both particles cease to exist. Their combined mass is converted entirely into energy, in the form of photons, usually 2 gamma-ray photons, flying off in opposite directions to conserve momentum. The total energy of these photons equals the combined mass energy of the electron and positron, plus any kinetic energy they had before the collision. Now, the mass of an electron is tiny, about 9.1 times 10 to the negative 31 kilograms. So the energy released by a single electron-positron annihilation is correspondingly small. But think about what would happen if you had a gram of antimatter, just 1 gram, less than the weight of a paperclip. If you could bring 1 gram of positrons together with 1 gram of electrons, the resulting annihilation would release about 180 trillion joules of energy. That's roughly equivalent to the energy released by about 43 kilotons of TNT, nearly 3 times the energy of the atomic bomb that destroyed Hiroshima. From a paperclip's worth of antimatter, the energy density of matter-antimatter annihilation is almost incomprehensibly high. It's hundreds of times more efficient than nuclear fission, and several times more efficient than nuclear fusion. In fact, it's the most energy-dense reaction known to physics, the most complete conversion of mass into energy that's physically possible. When matter and antimatter annihilate, they leave nothing behind. No ash, no waste, no residual matter, just pure energy. This is why antimatter shows up so often in science fiction. The idea of an antimatter drive, a spacecraft powered by controlled matter-antimatter annihilation, has been explored by everyone from Star Trek to serious NASA researchers. And the physics is sound. If you could produce and store enough antimatter, and if you could engineer a system to annihilate it with matter in a controlled way, the energy release would be extraordinary. A few milligrams of antimatter could, in principle, propel a spacecraft at significant speeds. But here's the reality check, and it's a big one. We can barely make antimatter at all, let alone in quantities useful for propulsion. The world's primary antimatter factory is CERN, the European Organization for Nuclear Research, located near Geneva, Switzerland. CERN's antiproton decelerator, yes, that's its real name, and it's exactly what it sounds like, produces antiprotons by slamming high-energy protons into a metal target. The collisions produce all sorts of particles, including antiprotons, which are then separated out, slowed down, and delivered to various experiments. And here's the thing about the quantities. CERN produces roughly 10 million antiprotons per minute. That sounds like a lot, until you realize how many antiprotons you'd need to make a measurable amount of antimatter. 10 million antiprotons weigh about 17 femtograms. That's 17 times 10 to the negative 15 grams. Essentially nothing. If CERN ran its antiproton production at full capacity, non-stop, for a year, it would produce roughly a nanogram of antiprotons, a billionth of a gram. At that rate, to produce a single gram of antimatter, just 1 gram, that paperclip's worth, would take something like 100 billion years. Longer than the age of the universe, by many times. And the cost? Various estimates have put the price of antimatter production at anywhere from $62 trillion per gram to hundreds of trillions per gram, depending on the efficiency assumptions. By any reasonable measure, antimatter is the most expensive substance in the universe, not just on Earth, in the universe, because making it requires such extraordinary energy input and such specialized equipment. And even if you could make it in useful quantities, you'd face the storage problem. How do you store something that will annihilate on contact with any form of ordinary matter? You can't put it in a jar. You can't put it in a box. Any container you build is made of matter, and the instant the antimatter touches it, both the antimatter and the container wall would annihilate in a flash of energy. The solution, at least for charged antimatter particles, is magnetic trapping. Since antiprotons and positrons have electric charge, they can be confined using electromagnetic fields, held in a vacuum, suspended by magnetic forces, never touching any physical surface. This is exactly what CERN's experiments do. The alpha experiment, for example, has trapped antihydrogen atoms for as long as 16 minutes, holding them in a magnetic bottle made of superconducting magnets, in an ultra-high vacuum, carefully balanced so that the anti-atoms float in the center of the trap without touching the walls. 16 minutes might not sound like much, but it's an extraordinary achievement. Antihydrogen is electrically neutral, so you can't use simple electric fields to trap it. Instead, alpha exploits the fact that antihydrogen atoms are very slightly magnetic. They have a tiny magnetic moment, and by creating a magnetic field that gets stronger toward the edges of the trap, they create a kind of magnetic bowl that the anti-atoms settle into. It's delicate, painstaking work, and the fact that it works at all is a testament to decades of experimental ingenuity. But we're talking about trapping a few dozen anti-atoms at a time, not grams, not milligrams, individual atoms, and even that pushes the limits of current technology. So antimatter is real, it's spectacularly energetic, and it's almost impossibly difficult to make and store. But you know what? You interact with antimatter more often than you might think, because antimatter has a practical application that affects millions of people every year, and it's happening in hospitals right now. PET scans, positron emission tomography. The P in PET stands for positron, the antiparticle of the electron, the very particle Carl Anderson discovered in 1932. Here's how it works. A patient is injected with a small amount of a radioactive tracer, usually a modified form of glucose, the sugar that cells use for energy. This tracer is labeled with a radioactive isotope, typically fluorine-18, which decays by emitting positrons. The positrons travel a very short distance, usually less than a millimeter, through the patient's body before encountering an ordinary electron. When the positron and electron meet, they annihilate, producing 2 gamma-ray photons that fly off in exactly opposite directions. The PET scanner is a ring of detectors surrounding the patient, and when 2 detectors on opposite sides of the ring register gamma rays at almost exactly the same time, the scanner knows that an annihilation event occurred somewhere along the line connecting those 2 detectors. By collecting thousands of these coincidence events, and processing them with sophisticated algorithms, the scanner can build up a three-dimensional map of where the tracer is concentrated in the body. And since cancer cells typically have higher metabolic rates than normal cells, they consume more glucose. The tracer tends to accumulate in tumors. So a PET scan can reveal the location, size, and metabolic activity of cancers, often before they're large enough to detect by other means. So there's a wonderful irony here. Antimatter, this exotic, seemingly science-fictional substance, has one of its most important real-world applications in saving lives. Every PET scan is antimatter at work. Every time a positron annihilates with an electron inside a patient's body, it's the same physics that Dirac predicted in 1928, that Anderson discovered in 1932, and that the Big Bang employed on a cosmic scale 13.8 billion years ago. The same physics, happening inside someone's body, producing images that help doctors find and fight cancer. Think about what that means. The physics of antimatter connects the first fractions of a second after the creation of the universe to the hospital down the road. The same principles, the same particles, the same annihilation process. Physics is one thing, happening everywhere, at every scale, all the time. Let me take you on another tangent, because this one is too fascinating to skip. Antimatter in space. You're lying there, maybe starting to drift a little, and I want you to imagine the space around Earth. Not the calm, empty void you might picture, but something much more dynamic. Earth is surrounded by what are called the Van Allen radiation belts, regions of charged particles trapped by Earth's magnetic field. Protons, electrons, all sorts of stuff, spiraling along magnetic field lines, bouncing back and forth between the poles. And in 2011, a satellite experiment called Pamela, the payload for antimatter-matter exploration and light nuclei astrophysics, because physicists love acronyms, detected a thin band of antiprotons trapped in the inner Van Allen belt. Antiprotons, just hanging out in the near-Earth space environment, caught in the planet's magnetic field. They're produced when high-energy cosmic rays smash into atoms in the upper atmosphere, creating particle-antiparticle pairs. Most of the antimatter produced this way annihilates almost immediately with nearby matter, but some of the antiprotons, being electrically charged, get caught by Earth's magnetic field before they hit anything. And there they sit, spiraling along field lines, until eventually they encounter a stray atom and annihilate. The quantities are tiny, estimated at only a few nanograms total, trapped in the Van Allen belts at any given time. But the fact that there is antimatter just hovering above our heads, right now, held in place by the magnetic field of our own planet, is one of those details that makes the universe feel wilder and stranger than you'd expect. Cosmic rays themselves are also a source of antimatter. When high-energy protons from deep space collide with interstellar gas, they can produce antiprotons, positrons, and other antiparticles. The Alpha Magnetic Spectrometer, or AMS-02, a particle physics detector mounted on the International Space Station since 2011, has been measuring the flux of cosmic ray positrons and antiprotons with unprecedented precision. And the results have been intriguing. AMS-02 has detected an excess of positrons at high energies, more positrons than you'd expect from standard cosmic ray production mechanisms. This excess is not fully understood. It could be produced by nearby pulsars, rapidly rotating neutron stars with intense magnetic fields that can accelerate particles to tremendous energies and produce positron-electron pairs. Or, more speculatively, it could be a signature of dark matter. Some theoretical models of dark matter predict that dark matter particles can annihilate with each other, producing ordinary matter and antimatter, including positrons. If the dark matter halo surrounding our galaxy contains particles that are slowly annihilating with each other, the resulting positrons would show up as an excess in cosmic ray measurements. AMS-02's data is tantalizingly consistent with some dark matter models, but it hasn't been possible to conclusively distinguish the dark matter explanation from the pulsar explanation. The measurements continue, the data accumulates, and the question remains open. And that's a beautiful thing about science. Sometimes the data tells you something surprising, and the answer turns out to be more complicated than you hoped. The universe doesn't always give you clean, definitive results. Sometimes it gives you a puzzle inside a puzzle, and you have to sit with the ambiguity for a while. Let me bring you back to the fundamental question now, because I've been circling around it, and I think you're ready for the deeper version. Why did the universe destroy almost all of its antimatter? We talked about the Sakharov conditions, the 3 necessary ingredients for generating a matter-antimatter asymmetry. We talked about CP violation, the experimental evidence for it, and the fact that the known CP violation in the standard model isn't strong enough. We touched on electroweak baryogenesis and leptogenesis as possible mechanisms. But let me go deeper into what we actually know, and what we're still trying to figure out. One of the most important things to understand is that the question isn't just, why is there more matter than antimatter? It's, why is there exactly this much more matter than antimatter? Because the ratio, the size of the asymmetry, is something we can measure, and it's expressed as a number called eta, the baryon to photon ratio. This is the ratio of the number of baryons, protons and neutrons, to the number of photons in the cosmic microwave background, and its value is about 6 × 10⁻⁻10, roughly 6 baryons for every 10 billion photons. That number, 6 parts in 10 billion, encodes the entire history of the matter-antimatter asymmetry. It tells you that for every 10 billion particle-antiparticle pairs that annihilated in the early universe, about 6 extra particles of matter survived. Those 6, multiplied across the vast volume of the observable universe, account for all the ordinary matter we see today. And here's what's remarkable. We can measure this number from 2 completely independent methods, and they agree. One method uses the cosmic microwave background, the detailed pattern of temperature fluctuations in the afterglow of the Big Bang, as measured by satellites like COBE, WMAP, and Planck. The physics of how the CMB was produced depends sensitively on the baryon to photon ratio, so by analyzing the CMB power spectrum, cosmologists can extract the value of eta. The other method uses Big Bang nucleosynthesis, the process by which the lightest elements, hydrogen, helium, deuterium, lithium, were formed in the first few minutes after the Big Bang. The abundances of these elements depend critically on how many baryons there were relative to photons, so by measuring the primordial abundances of these elements and comparing them to theoretical predictions, you can independently determine eta, and the 2 methods agree. Both give a value of about 6 × 10⁻⁻10. This concordance is one of the great triumphs of modern cosmology. It tells us that our understanding of the early universe, from about 1 second after the Big Bang onward, is on solid ground. We understand the physics well enough to predict the correct ratio from 2 completely different observational windows. But what we don't understand is how that ratio got set in the first place. What process, operating in the first fractions of a second, before nucleosynthesis, before the CMB was produced, generated exactly that asymmetry? That's the open question, and it's a quantitative question, not just a qualitative one. It's not enough to find a mechanism that produces some asymmetry. You need a mechanism that produces exactly the right amount. Let me tell you about another layer of this puzzle, because it involves one of the most profound theoretical results in all of physics. It's called the CPT theorem, and it says something extraordinary. Even though C symmetry is violated, The universe distinguishes matter from antimatter. Even though p symmetry is violated, the universe distinguishes left from right. Even though CP symmetry is violated, the combined operation of swapping matter for antimatter and flipping left to right is not a perfect symmetry either. Even though all of these individual symmetries are broken, the CPT theorem says that the combination of all three, charge conjugation, parity, and time reversal, applied simultaneously, is an exact symmetry of nature. CPT symmetry means that if you take any physical process, swap all particles for antiparticles, flip all spatial coordinates, and reverse the direction of time, you get a valid physical process. And this isn't just a guess or an experimental observation. It's a mathematical theorem, derived from very general principles of quantum field theory. As long as the theory obeys certain basic requirements, like Lorentz invariance, the laws of physics are the same in all inertial reference frames, and locality. Interactions happen at specific points in space. CPT symmetry must hold. This has profound implications. If CPT is an exact symmetry, then the mass of any particle must be exactly equal to the mass of its antiparticle, not approximately, exactly, to infinite precision. The same goes for the lifetime and for the magnitude, but not the sign, of the electric charge. If anyone ever measured a difference between the mass of an electron and the mass of a positron, it would violate CPT symmetry, and that would shake the foundations of quantum field theory itself. And this is one of the reasons Kern's experiments with antihydrogen are so important. By precisely measuring the properties of antihydrogen, its mass, its spectrum, how it interacts with gravity, and comparing them to ordinary hydrogen, physicists are testing CPT symmetry with extraordinary precision. So far, every measurement is consistent with CPT being exactly right. The spectrum of antihydrogen matches the spectrum of hydrogen. The charge-to-mass ratio of the antiproton matches the protons to better than 1 part in a billion. But physicists keep pushing, because if CPT were violated, even by a tiny, almost imperceptible amount, it would point to fundamentally new physics. It would mean that the most basic assumptions of quantum field theory need revision, and in a field where the standard model has been frustratingly successful, where every experiment seems to confirm the theory rather than break it, a CPT violation would be one of the most exciting discoveries imaginable. Now, here's something I want to circle back to, because I think it's important and I didn't give it enough space earlier. Let me talk about what antimatter feels. And by that, I mean, what does gravity do to antimatter? For almost everything we've discussed, antimatter behaves exactly like matter, with some signs flipped. Same mass, opposite charge. Same interactions with the strong force and the weak force, and the electromagnetic force. But what about gravity? Does antimatter fall down the same way matter does? Or does it fall up? Does antimatter have anti-gravity? This might sound like a silly question. General relativity, Einstein's theory of gravity, says that all forms of energy and mass gravitate the same way. There's no room in general relativity for anti-gravity. Matter curves space-time, and everything, including antimatter, follows those curves. Antimatter should fall down, just like matter. But here's the thing. Until very recently, nobody had actually tested this directly. And in physics, you don't get to assume something is true just because your theory says so. You have to check, especially when the stakes are this high. Because if antimatter did fall up, if it experienced gravity in the opposite direction from matter, it would have enormous implications. It could potentially explain why matter and antimatter separated in the early universe. It could mean that antimatter and matter gravitationally repel each other, which would be a revolutionary discovery. And so physicists at CERN set out to test it. The AlphaGo experiment, a variant of the Alpha experiment specifically designed to study antimatter in gravitational fields, was built to watch how anti-hydrogen atoms behave when you turn off the magnetic trap and let them fall. Do they fall down, toward the Earth, or do they drift up, away from it? The result came in 2023, and anti-hydrogen falls down, just like regular hydrogen, just like everything else. Antimatter responds to gravity in the same direction as matter, exactly as general relativity predicts. The measurement wasn't super precise, the uncertainty was still significant, but the direction was clear. Antimatter falls toward the Earth, no anti-gravity. And I mention this not because the result was surprising. Most physicists expected exactly this outcome, but because the fact that someone actually went and checked is one of the things I love about physics. It's not enough to believe something because the theory says so. You have to look. You have to build the experiment, do the measurement, and let nature tell you the answer. And sometimes nature confirms what you expected, and sometimes it doesn't. And either way, you've learned something real. Let me take you somewhere else now. Let me tell you about one of the most beautiful experiments in the history of antimatter research, and one that connects directly to the question of why the universe destroyed its antimatter. In the late 1990s and early 2000s, two experiments at facilities on different continents, Babar at SLAC in California and Bell at the KEK laboratory in Japan, were built specifically to study CP violation in a system called the B meson. B mesons are particles that contain a bottom quark, also called a beauty quark, which is where the B comes from, paired with another quark. They're produced copiously in high-energy electron-positron collisions, and they're particularly useful for studying CP violation because the theoretical predictions for how CP violation manifests in B meson decays are very precise. These were big experiments. Babar and Bell each involved hundreds of physicists, and the accelerators that powered them were custom-built. SLAC's PEP2 accelerator produced electron-positron collisions at a precisely tuned energy, the energy needed to produce pairs of B mesons and anti-B mesons. And the key trick was to make the two beams asymmetric. The electrons and positrons had different energies, so the B mesons produced in the collision were moving, and their decays were spread out in space, making it possible to measure the tiny time differences between B and anti-B meson decays. And what Babar and Bell found was exactly what the Standard Model predicted. CP violation in B meson decays was observed, at precisely the level predicted by the CKM matrix. It was a triumph for the Standard Model, one of its most precise predictions, confirmed beautifully by experiment. But it was also, in a way, a disappointment. Because the CP violation in B mesons, like the CP violation in kaons, is too small to explain the matter-antimatter asymmetry of the universe. The Standard Model works. It predicts CP violation, and the predictions match observations. But the total amount of CP violation it contains falls short of what's needed by many orders of magnitude. The Standard Model describes nature accurately, but nature seems to need more CP violation than the Standard Model provides. This is sometimes called the baryogenesis problem, and it's one of the strongest reasons physicists believe there must be physics beyond the Standard Model. Not because the Standard Model is wrong, it's spectacularly right about almost everything, but because it's incomplete. There must be additional particles, additional interactions, additional sources of CP violation that we haven't discovered yet. The universe is telling us, through its very existence, that there's more to the story than what we currently know, and the search for that missing physics is one of the most active areas of research in particle physics today. Experiments at the Large Hadron Collider at CERN the most powerful particle accelerator ever built, are searching for new particles that could provide additional sources of CP violation. The LHCb experiment, in particular, is designed to study CP violation in the decays of particles containing bottom and charm quarks, looking for deviations from the Standard Model's predictions. So far, the results have been tantalizingly consistent with the Standard Model, but the measurements are getting more precise every year, and there's always the possibility that the next round of data will reveal something unexpected. Meanwhile, neutrino experiments are pursuing the leptogenesis angle. If the matter-antimatter asymmetry was originally generated in the neutrino sector and then converted to the baryon sector via Sphaleron processes, then CP violation in neutrino oscillations would be a crucial piece of evidence. Experiments like T2K in Japan and NOVA in the United States have been measuring neutrino and antineutrino oscillation rates, looking for differences that would indicate CP violation. And the early results are suggestive. They hint at a large CP violating phase in the neutrino sector, much larger than the CP violation in the quark sector. But the statistical significance isn't conclusive yet, and the next generation of experiments, particularly DUNE, the Deep Underground Neutrino Experiment, which is being built in the United States, with a particle beam traveling from Fermilab in Illinois to a detector deep underground in South Dakota, will have the precision needed to make a definitive measurement. If DUNE confirms large CP violation in the neutrino sector, it won't prove leptogenesis, the connection between low-energy neutrino CP violation and the high-energy processes that occurred in the early universe is complicated and model-dependent, but it would be a powerful piece of circumstantial evidence. It would tell us that the neutrino sector does contain the kind of CP-violating physics that leptogenesis requires, even if we can't directly observe the high-energy processes themselves. Let me slow down for a moment and talk about something that I think gets lost in the technical details: the emotional weight of this question. You're lying there, maybe your eyes are closed now, and I want you to think about what it means that you exist because of a flaw. Not a design, a flaw, an imperfection in the symmetry of the universe. If the laws of physics were perfectly symmetric between matter and antimatter, you wouldn't be here. Nobody would be here. Nothing would be here. The universe would be a cold, uniform bath of radiation, expanding forever into darkness. But the symmetry isn't perfect. It's broken, ever so slightly, by an amount so small that it's almost invisible, about 1 part in a billion. And that imperfection, that tiny crack in the cosmic mirror, is the reason there are stars and planets and oceans and forests and cities and love songs and arguments and dreams. Everything, all of it, traced back to a symmetry that almost, but not quite, held. There's something deeply moving about that, I think. The idea that existence itself depends on an imperfection, that the universe is not the clean, symmetric place it should be, and that its asymmetry is what makes it interesting, what makes it anything at all. Physicists sometimes talk about the anthropic implications of this, the idea that if the asymmetry had been even slightly different, the universe would look radically different. If it had been smaller, there would be less matter, fewer galaxies, fewer stars. If it had been 0, there would be nothing. If it had been much larger, well, that's an interesting question. A much larger asymmetry would mean more matter survived, but it would also mean the conditions in the early universe were different, affecting things like the formation of the lightest elements and the growth of cosmic structures. The value we observe, about 6 parts in 10 billion, seems to be in a range that allows for a rich, complex universe. Whether this is a coincidence, a consequence of some deeper principle, or something that requires an explanation beyond physics as we currently understand it, is itself an open question. Let me come back to the practical side for a moment. Because I want to tell you about the most precise measurement of antimatter ever made. And it's one of those stories that shows how patient and meticulous science can be. The BASE experiment at CERN, that stands for Baryon-Antibaryon Symmetry Experiment, has been measuring the magnetic moment of the antiproton with extraordinary precision. The magnetic moment is a measure of how strongly a particle interacts with a magnetic field, and it's one of the fundamental properties of a particle. The Standard Model, combined with quantum electrodynamics, predicts the magnetic moment of the proton and antiproton to high precision, and any difference between them would violate CPT symmetry. What BASE does is remarkable. They trap a single antiproton, one individual antiparticle, in a device called a penning trap, which uses a combination of electric and magnetic fields to confine the particle in a tiny region of space. The antiproton bounces back and forth in the trap, and by measuring the frequencies of its motion with extreme precision, the experimenters can determine its magnetic moment. And they've found that the magnetic moment of the antiproton matches the magnetic moment of the proton to a precision of about 1.5 parts per billion, 1.5 parts in a billion. The agreement is stunning. It means that, to the best of our ability to measure, the antiproton is a perfect mirror image of the proton, exactly as CPT symmetry demands. This kind of measurement is what I mean when I talk about precision physics. It's not flashy. It's not the kind of experiment that makes headlines. Scientists confirm that antimatter behaves exactly as expected is not a very exciting newspaper headline. But the precision itself is extraordinary, and the fact that the agreement holds to 9 decimal places is telling us something profound about the structure of the universe. It's telling us that the symmetry between matter and antimatter at the level of individual particle properties is extraordinarily exact. Whatever broke the balance in the early universe did so in a subtle, delicate way, not by making antimatter fundamentally different from matter, but by tweaking the processes that created them so slightly that an almost imperceptible excess of matter survived. And I think that subtlety is part of what makes this mystery so compelling. It's not a big, obvious asymmetry. It's not like matter and antimatter are radically different and one simply won out. They're almost identical. The asymmetry that gave rise to the entire physical universe is one of the smallest effects in all of physics, and yet its consequences are everything. Let me tell you about one more experiment, because it's happening right now, and it's one of the most ambitious antimatter experiments ever conceived. It's called AEGIS, the Anti-Hydrogen Experiment, Gravity, Interferometry, Spectroscopy, and it's at CERN, alongside alpha and BASE, and a whole ecosystem of antimatter experiments. AEGIS is designed to measure the effect of gravity on antimatter with much higher precision than the alpha-G measurement I mentioned earlier. The basic idea is to create a beam of anti-hydrogen atoms, not trapped atoms, but a directed stream of them, and watch how the beam curves as it falls under gravity. By measuring the deflection of the beam very precisely, they can determine whether antimatter falls at exactly the same rate as matter, or whether there's a tiny difference. Why would there be a difference? Well, in standard general relativity, there shouldn't be. The equivalence principle, one of the cornerstones of Einstein's theory, says that all objects fall at the same rate in a gravitational field, regardless of their composition or type of matter. But some speculative theories of quantum gravity suggest that there could be a tiny difference, a violation of the equivalence principle for antimatter, that might be detectable with sufficiently precise measurements. A confirmed violation would be a revolutionary discovery, pointing to new physics beyond both the Standard Model and general relativity. The experiments are ongoing, and so far no violation has been detected. But the precision is improving, and the search continues. And that's the rhythm of experimental physics. You build a better experiment, you push to higher precision, and either you find something new or you rule out a larger class of theories. Both outcomes are valuable. Both advance knowledge. Now, I realize I've been talking a lot about the physics and the experiments, but I haven't fully addressed one of the most basic questions someone might have about antimatter, and it's a question that gets at something surprisingly deep. If matter and antimatter annihilate when they meet, and if the universe started with roughly equal amounts of both, why didn't they find each other and annihilate immediately? What allowed some matter to survive long enough to form atoms and stars and planets? The answer lies in timing and temperature. In the very early universe, the first microsecond or so after the Big Bang, the temperature was so unimaginably high that particles and antiparticles were being created and destroyed constantly. Every time a pair annihilated, the resulting energy could immediately produce a new pair. It was a dynamic equilibrium, creation and annihilation, happening at equal rates with no net change. Think of it like a boiling pot of water, where molecules are constantly escaping into steam and condensing back into liquid, and the total amount of water stays roughly constant. But the universe was expanding, and as it expanded, it cooled. And as it cooled, the average energy of the particles dropped. There came a critical moment, different for each type of particle, depending on its mass, when the temperature dropped below the threshold needed to create new particle-antiparticle pairs. After that point, no new pairs were being created, but the existing particles and antiparticles could still find each other and annihilate. And they did, prolifically, efficiently, almost completely. But almost is the key word. Because of the tiny asymmetry we've been discussing, that one extra matter particle per billion, the annihilation wasn't quite complete. After all the pairs had found each other and destroyed each other, there was a small residue of matter left over, and that residue had no antimatter to annihilate with, so it survived. It cooled, it clumped together under gravity. It formed atoms, then molecules, then gas clouds, then stars, then planets. Then eventually, after 13.8 billion years of cosmic evolution, you. The timing was crucial. The asymmetry had to be established before the annihilation epoch, before the temperature dropped below the pair production threshold. If the asymmetry developed later, there would have been nothing to save. All the matter and antimatter would have already annihilated, leaving only photons. The asymmetry had to be baked in from the very earliest moments, when the universe was less than a billionth of a second old. And this is why the question of baryogenesis, the origin of the matter-antimatter asymmetry, is so tightly connected to the physics of the very early universe. Whatever process created the asymmetry had to operate at the highest energies, in the hottest conditions, in the first fractions of a second after the Big Bang. And that's a regime where our theoretical understanding is least certain, where the physics may involve forces and particles we haven't yet discovered, and where direct experimental tests are hardest to perform. It's humbling when you think about it. The question of why you exist, why anything exists, comes down to physics that happened in less than a billionth of a second, at temperatures we can barely imagine, involving processes we can't yet fully describe. And yet here we are, 13.8 billion years later, lying in bed, thinking about it. Let me pause on something that often comes up when people hear about antimatter for the first time: the question of antimatter weapons. Science fiction loves this idea, and it's easy to see why. If a gram of antimatter releases energy equivalent to 43 kilotons of TNT, then surely a few kilograms could destroy a city. And yes, in a purely theoretical sense, that's true. A kilogram of antimatter annihilating with a kilogram of matter would release about 43 megatons of energy, roughly the yield of the Tsar Bomba, the largest nuclear weapon ever detonated. The energy density is real, But the practical barriers make this a non-concern for the foreseeable future. Remember those production numbers I mentioned earlier? CERN produces roughly a nanogram per year, and the cost runs into the tens of trillions per gram. Even if you imagined some radical breakthrough in production efficiency, you'd still face the storage problem. Any containment failure, any magnetic glitch, any power interruption, any microscopic leak in the vacuum, and your antimatter contacts the container wall and annihilates. There's no safe way to store significant quantities of antimatter with current or foreseeable technology, and the energy required to produce the antimatter in the first place is always greater than the energy you'd get back from annihilating it. Conservation of energy guarantees that. You can't create a net energy gain by making antimatter and then destroying it. You always spend more energy than you recover, because the production process is inefficient. So antimatter as a weapon or a fuel source remains firmly in the realm of science fiction, not because the physics doesn't work, but because the engineering is impossible at any remotely achievable scale. The interesting physics isn't about what we could do with antimatter if we had lots of it. It's about what the existence of antimatter tells us about the structure of reality. And on that note, let me tell you about one of the most beautiful reinterpretations in the history of physics, because it connects antimatter to something you wouldn't expect, the nature of time itself. In 1949, Richard Feynman, brilliant, irreverent, bongo drum-playing Richard Feynman, proposed a radical new way of thinking about antiparticles. Dirac's original picture, with the sea of negative energy electrons filling all of space, was mathematically useful but physically bizarre. Feynman suggested a different interpretation, one that has become the standard way physicists think about antimatter today. Feynman's idea was this: a positron, the antiparticle of the electron, can be thought of as an electron traveling backward in time. Now, before you object, let me explain what that means, because it's not as crazy as it sounds. In the mathematical formalism of quantum field theory, the equations that describe a positron moving forward in time are mathematically identical to the equations describing an electron moving backward in time. The two descriptions are completely equivalent. They predict the same observations, the same experimental results, the same everything. It's not that positrons really travel backward in time in any physical sense. It's that the mathematics doesn't distinguish between the two descriptions. They're the same calculation, written in two different languages. Feynman used this insight to develop his famous Feynman diagrams, the simple, elegant pictorial representations of particle interactions that have become one of the most iconic tools in all of physics. In a Feynman diagram, particles are represented by lines and interactions by vertices where lines meet. And in this framework, an antiparticle is drawn as a particle line going backward in time. Literally, the arrow on the line points in the opposite temporal direction. This isn't just a notational trick. It has deep physical content. It means that, at the level of fundamental processes, the creation of a particle-antiparticle pair can be reinterpreted as a single particle making a U-turn in time, an electron zipping forward in time, suddenly reversing direction and heading backward in time, which looks, to us, like a positron appearing and moving forward in time alongside the electron. The pair creation event is a turning point. The annihilation event, when the electron and positron meet and destroy each other, is the electron completing the U-turn and heading forward in time again. It's a perspective that Feynman himself described as just as good as the conventional picture, not better or truer. Physics doesn't tell you which interpretation is really correct. It only tells you what the observations will be, and both interpretations predict the same observations. But there's something deeply suggestive about the time reversal picture. It hints at a connection between the direction of time and the distinction between matter and antimatter, that may run deeper than our current theories fully capture. And speaking of deep connections, there's one more idea I want to mention before we move on, because it's one of those, wait, what? Moments that make physics so delightful. In 1963, a physicist named John Wheeler, who was also Feynman's doctoral advisor, incidentally, proposed something called the one-electron universe hypothesis. It's not a serious scientific theory, more of a thought experiment, but it's so wonderfully strange that it's worth knowing about. Wheeler suggested that maybe there's only one electron in the entire universe, just one, and the reason we see trillions upon trillions of electrons everywhere is that this single electron is zigzagging back and forth through time. When it's moving forward in time, it looks like an electron. When it reaches the far future, it turns around and heads backward in time. And on the backward journey, it looks like a positron. Then it reaches the far past, turns around again, and comes forward as another electron. And so on, over and over, tracing a fantastically convoluted path through space-time, appearing at each point in time as an electron or a positron, depending on which direction it's traveling. In this picture, every electron in the universe is the same electron, and every positron is also the same electron, just on a return trip. The reason every electron has exactly the same mass and charge would be trivially explained. They're all the same particle. It's a beautiful idea, and Feynman later acknowledged that Wheeler had mentioned it to him over the phone. But there's a fatal flaw. If it were true, there should be exactly as many positrons in the universe as electrons, since every forward pass creates one electron, and every backward pass creates one positron. But there are far more electrons than positrons in the observed universe. So the one-electron hypothesis doesn't work as stated. Still, as a thought experiment, it captures something profound about the deep connection between antimatter and the direction of time, and it illustrates the kind of radical, playful thinking that sometimes leads to genuine insight in physics. Let me tell you about something else that I find endlessly fascinating, and it's one of those ideas that seems simple on the surface, but opens up a rabbit hole when you start pulling at it. Can antimatter exist in large quantities somewhere in the universe? Could there be anti-stars, anti-galaxies, entire regions of the cosmos made of antimatter that we simply haven't detected yet? This was actually a serious proposal for a while. In the 1960s and 70s, some physicists suggested that maybe the universe doesn't have a matter-antimatter asymmetry at all. Maybe it made equal amounts of both, and they simply separated. Perhaps during the expansion of the early universe, regions of matter and regions of antimatter drifted apart, and what we see as our matter-dominated observable universe is just one patch in a much larger cosmos that's perfectly symmetric overall. Maybe there are anti-galaxies out there, billions of light-years away, and we just can't tell from this distance. It's a clever idea, but there's a serious problem with it. If there were large regions of antimatter and matter adjacent to each other, they would meet at the boundaries. And at those boundaries, annihilation would occur on a massive scale. Matter atoms from one region would drift across the border and encounter antimatter atoms from the other, and the resulting annihilation would produce intense gamma radiation, a very specific type of gamma radiation, with a characteristic energy corresponding to the mass of the annihilating particles. And we've looked for that radiation. We've searched the sky for the telltale gamma-ray signature of large-scale matter-antimatter annihilation, and we haven't found it. Not at galactic boundaries, not at cluster boundaries, not anywhere. The observed gamma-ray background is consistent with known astrophysical sources. No sign of the massive annihilation zones that would exist if significant regions of antimatter were out there. Moreover, Cosmic rays provide another test. Cosmic rays from distant sources travel across the galaxy and beyond, passing through the interstellar and intergalactic medium. If they passed through a region of antimatter, they would annihilate, and we'd see the products. But the cosmic rays we observe are overwhelmingly matter. The antiprotons and positrons we detect in cosmic rays are present at levels consistent with secondary production. They're the byproducts of high-energy collisions, not the residents of anti-galaxies. The AMS-02 experiment on the International Space Station has been specifically looking for anti-helium nuclei in cosmic rays. If anti-stars existed, they would presumably undergo anti-nucleosynthesis, fusing anti-hydrogen into anti-helium, just as ordinary stars fuse hydrogen into helium. And some of that anti-helium might escape into the cosmic ray flux and eventually reach our detectors. AMS-02 has reported a few candidate events that might be anti-helium, but the numbers are so small that they could easily be instrumental artifacts or misidentified background events. As of now, there's no confirmed detection of cosmic ray anti-helium, which puts tight constraints on how many anti-stars, if any, could exist in our galaxy or nearby. So the evidence strongly suggests that our observable universe is overwhelmingly, perhaps exclusively, made of matter. The antimatter is gone. It was destroyed in the first seconds after the Big Bang, and what we see today, the stars, the galaxies, the gas clouds, you and me, is the tiny residue that survived. And there's something both sobering and awe-inspiring about that picture. Everything you've ever seen, everything you've ever touched, every person you've ever known, every object in every museum, every building in every city, every mountain and ocean and forest and desert, on every planet around every star in every galaxy, all of it is a remnant, a leftover, the tiny fraction that survived the greatest annihilation in the history of the universe. Let me take you down one more path before we start to wind down, because there's a question that sometimes comes up and it's more subtle than it seems. What exactly determines whether a particle is matter and its partner is antimatter? Is there something inherently special about the particles we call matter? Could the labels be swapped? And the answer is, in a sense, yes. The labels are, to a large degree, conventional. We call electrons matter and positrons antimatter because electrons are what we're made of. But there's nothing inherently more fundamental about an electron than a positron. If the asymmetry had gone the other way, if there had been one extra antiparticle per billion instead of one extra particle, the universe would have ended up made of what we currently call antimatter. And the beings living in that universe would call their stuff matter, and our stuff antimatter. The physics would be identical. The labels are anthropocentric, not physical. This is actually a consequence of the CPT symmetry we discussed earlier. If you applied CPT to the entire universe, swapped every particle for its antiparticle, reflected all spatial coordinates, and reversed time, you'd get a universe that obeys all the same laws as ours. It would look different in detail. Our baryons would be replaced by antibaryons, our electrons by positrons, but the physics governing it would be indistinguishable. The matter-antimatter distinction is real, in the sense that particles and antiparticles are physically distinct objects with opposite charges, but the question of which one we call matter and which one we call antimatter is just a naming convention, based on the historical accident that we're made of one and not the other. Now, this might seem like a purely philosophical point, but it actually has a deeper significance. It tells us that the matter-antimatter asymmetry of the universe is not about matter being better or more natural than antimatter. It's about a process, an event or a series of events in the early universe that happened to favor one over the other. If those events had gone the other way, With the CP violation pointing in the other direction, we'd have an anti-universe, and it would work just fine. The asymmetry is contingent, not necessary. It's a feature of the history of our particular universe, not a feature of the laws of physics themselves. And that raises yet another question, one that edges into the truly speculative. Could there be other universes, perhaps as part of a multiverse, where the asymmetry went the other way, where antimatter won instead of matter? Some models of eternal inflation and the multiverse suggest that different regions of spacetime might have different local asymmetries, depending on how the relevant fields and symmetry-breaking processes played out in each region. In some patches, matter wins. In others, antimatter wins. In still others, the asymmetry might be zero, and those regions would be empty, devoid of atoms, devoid of structure, devoid of observers. It's a speculative idea, deeply uncertain, but it's one of those thoughts that makes you appreciate how contingent our existence might be. But let's pull back from the speculative edge and talk about something a little more grounded. Let me tell you about the Standard Model's mechanism for CP violation, because it's a piece of physics that doesn't get enough appreciation, and it's one of those things that's surprisingly elegant when you understand it. The CP violation in the Standard Model comes from the weak force, specifically, from the way the weak force interacts with quarks. In the Standard Model, there are 6 types of quarks, arranged in 3 generations. The first generation contains the up and down quarks, the building blocks of protons and neutrons. The second generation contains the charm and strange quarks. The third generation contains the top and bottom quarks. Each generation is heavier than the one before. Now, the weak force has a peculiar property. When it acts on a quark, it can change that quark's flavor. An up quark can emit a W boson and become a down quark. A charm quark can become a strange quark, and so on. But the transformations don't strictly respect the generational boundaries. An up quark can become a down quark, but it can also, with smaller probability, become a strange quark or a bottom quark. The weak force mixes the generations. This mixing is described by a mathematical object called the CKM matrix, named after Nicola Cabibbo, who first described the mixing between 2 generations, and Makoto Kobayashi and Toshihide Masukawa, who extended it to 3 generations in 1973. The CKM matrix is a 3x3 grid of complex numbers that tells you the probability of each quark flavor transforming into each other quark flavor under the weak force. And here's the key insight. When you have 3 generations of quarks, the CKM matrix contains a parameter that can't be removed, a complex phase, called the CP violating phase. This phase is what makes certain weak force processes proceed at different rates for matter and antimatter. It's the mathematical source of CP violation in the Standard Model. Kobayashi and Masukawa's insight in 1973 was remarkable. At the time, only 3 quarks were known: up, down, and strange. The charm quark had been predicted, but not yet discovered. And the third generation, the top and bottom quarks, was entirely hypothetical. But Kobayashi and Masukawa showed that you needed at least 3 generations of quarks for CP violation to occur in the Standard Model. 2 generations weren't enough. The CKM matrix for 2 generations has no room for a CP violating phase. 3 generations are the minimum. And this prediction was confirmed, spectacularly, over the following decades. The charm quark was discovered in 1974, the bottom quark in 1977, the top quark in 1995. All 3 generations exist, and the CKM matrix has been measured in exquisite detail by experiments around the world. Kobayashi and Masukawa won the Nobel Prize in 2008 for a prediction they made in 1973, when most of the particles it relied on hadn't even been discovered yet. Think about that. They predicted that 3 generations of quarks were needed for CP violation, at a time when only 1 generation was fully confirmed. And they were right. The mathematics told them what nature required, and nature eventually confirmed it. It's another one of those moments, like Dirac predicting the positron, where the equations contain truths that experiment hadn't yet revealed. But I want to be honest about where this leaves us, because the story of antimatter and the matter-antimatter asymmetry is a story that does not yet have an ending. We know what antimatter is. We can make it, trap it, measure it, study its properties with incredible precision. We know that it's a nearly perfect mirror image of matter. We know that the early universe made equal amounts of both, and that almost all of it annihilated, leaving behind the tiny residue that constitutes the entire physical universe. We know that the survival of matter required a broken symmetry, CP violation, and we've found CP violation in the Standard Model, in kaons, in B mesons, in the structure of the CKM matrix. We know the Sakharov conditions that any theory of baryogenesis must satisfy, but we don't know how it happened. The CP violation we've measured isn't strong enough. The Standard Model, for all its brilliance, can't explain the specific amount of asymmetry we observe. Something beyond the Standard Model is needed. New particles, new forces, new sources of CP violation that we haven't found yet. And the search continues. At the Large Hadron Collider, physicists are pushing the precision of CP violation measurements to unprecedented levels, looking for the tiniest deviations from Standard Model predictions. At neutrino experiments around the world, researchers are probing the neutrino sector for CP violation that could support leptogenesis. At CERN's antimatter facility, experiments are testing the properties of antihydrogen and antiprotons with ever-increasing precision, looking for any hint of a difference between matter and antimatter that might point to new physics. And theorists are exploring models, from supersymmetry to extra dimensions to extended Higgs sectors, that could provide the missing ingredients. It's a field in motion, alive with questions and possibilities. And one of the most remarkable things about it is how much it connects. The question of why there's more matter than antimatter ties together particle physics and cosmology, laboratory experiments and the earliest moments of the universe, the properties of individual particles and the large-scale structure of everything. It's one of those questions that sits right at the intersection of what we know and what we don't, linking the established physics of the Standard Model to the unknown physics that must lie beyond it. And here's what I want you to take with you as you drift off. The next time you look at anything, your hand, a tree, a star, remember that what you're looking at is a survivor. It's the matter that made it through the great annihilation. The antimatter that was its mirror twin is gone, converted to photons that still fill the universe as the cosmic microwave background, a faint whisper of everything that was destroyed. What remains, what you are, is the residue, the imperfection, the beautiful, unexplained flaw in the symmetry that should have been perfect but wasn't. And maybe, in a way, that's the most comforting thought of all. The universe isn't perfect. Its imperfection is not a failure. It's the reason there are sunsets and symphonies, and people who lie awake at night wondering how it all works. The asymmetry that created you is tiny, less than 1 part in a billion, and nobody fully understands where it came from. But it's there, and because it's there, everything else is too. The antimatter is gone, destroyed in the first seconds of the universe, in the most complete annihilation imaginable. But its ghost lingers, in the cosmic microwave background that bathes the sky, in the equations that predict its existence, in the experiments that created anew in laboratories deep underground, in the PET scans that save lives in hospitals, in the positrons trapped above our heads in the Van Allen belts, and in the deep, unsolved mystery of why nature favored matter by the slimmest of margins. You exist because of a question that hasn't been answered yet, and that's not unsettling. It's wonderful. It means the story isn't over. It means there's still something fundamental to discover about why the universe is the way it is. Somewhere out there, in the data from the next generation of experiments, in the mathematics of a theory not yet formulated, in the observations of a telescope not yet built, the answer is waiting. And maybe, just maybe, when we find it, it will be as beautiful and unexpected as everything else in this story. As unexpected as Dirac, sitting at his desk in Cambridge, discovering antimatter hidden in an equation. As unexpected as Anderson, photographing a track in a cloud chamber that curved the wrong way. As unexpected as the universe itself, emerging from a perfect symmetry that broke just enough to create everything we know and love. The particles and antiparticles that annihilated in those first seconds. They're gone. But the light they left behind is still here, filling the cosmos with a gentle glow. And you're here too, made of the matter that survived, lying in the dark, thinking about things that happened billions of years before the Earth existed. And there's something deeply peaceful about that, I think. You are connected, through physics, through the atoms in your body, to the first moments of creation. You are the universe's way of surviving its own annihilation. Let your eyes close. Let the weight of your body settle into the bed. The atoms in the pillow under your head, the protons and neutrons and electrons that make up everything you're touching, they are the descendants of that ancient asymmetry. They carry in them the memory of a battle that was won by the narrowest possible margin, a victory measured in parts per billion. And somewhere out there, in laboratories and observatories, and the minds of physicists who can't sleep because they're thinking about exactly these questions, the search for the answer continues. The universe keeps its deepest secrets close, but it also leaves clues. In the spectrum of antihydrogen, in the oscillations of neutrinos, in the faint glow of the cosmic microwave background, in the mathematics that describes the forces of nature. The clues are there, scattered across the cosmos and the equations, waiting for someone to put them together. The antimatter is gone, but the question of where it went and why is one of the most beautiful mysteries in all of science. And as you lie here, breathing quietly, you are both the evidence and the detective. You are the proof that the symmetry broke, and you are the mind asking why. That's a pretty good place to be, all things considered. The matter that makes you, every atom, every proton, every quark, has been on a journey of 13.8 billion years to reach this moment. It started in the furnace of the Big Bang, survived the Great Annihilation, was forged in the cores of ancient stars, scattered across space in supernova explosions, pulled together by gravity to form new stars and planets, and eventually assembled into the molecules and cells and tissues that make up you. And through all of that, all 13.8 billion years of it, the fundamental question of why there was any matter left to begin with has remained unanswered. But the atoms in your body don't know that. They just keep doing what atoms do, bonding, vibrating, conducting electricity, absorbing light, holding you together. They don't care about the mystery of their own existence. That's your job, and you can do it tomorrow, or the next day. There's no rush. For now, the universe is here. You are here. The antimatter is gone, but the story it left behind is one of the most remarkable stories ever told. A story of symmetry and breaking, of creation and destruction, of the tiniest imperfection giving rise to everything. And you are part of that story. You are, quite literally, made of the plot twist. So rest. Let the weight of it all settle. The quarks and leptons and photons will still be there in the morning, doing their thing, obeying their equations, holding the world together the way they've been doing since the beginning. And the mystery, that beautiful, stubborn, unsolved mystery of why there's something rather than nothing, will still be waiting too. It's been waiting for 13.8 billion years. It can wait one more night. Sleep well. You are stardust. You are the leftovers of the greatest fire in the history of existence. And you are, in a very real and precise sense, the universe's most unlikely survivor. Good night.